Throughout this chapter, we've been discussing eigenvalues and eigenvectors, and then we spent the last number of videos talking about how we can use those to set up this diagonalization procedure to solve differential equations, to do the quadratic form, and so forth. Now we're going to change directions a little bit and discuss decomposition of matrices, or sometimes we refer to it as factorization. The idea is we're going to take a matrix A, general matrix A, and then we want to be able to factorize it into the product of multiple matrices. Usually those matrices have some desirable properties which allow us to do further analysis or solve the system or whatever the application demands. In fact, the diagonalization procedure itself that we've been looking at is an example of, or can be framed as an example of, a matrix decomposition in the following way. So we'll call it an eigen decomposition. So we're taking a square matrix A. Obviously, only square matrices have eigenvalues, eigenvectors, and can be diagonalized. So we're taking a square matrix A, and we have the following three possible decompositions, or eigen decompositions. So in the case of a real symmetric matrix with distinct eigenvalues, we know that the eigenvectors will be mutually orthogonal. We can normalize them and form a modal matrix Q, which is orthogonal. So in that case, we had that our diagonal matrix D, which has the eigenvalues of A down the diagonal, was equal to Q transpose times A times Q. And if we just simply flip that around, we can write that as A is equal to Q D Q transpose. So we have decomposed A, the square matrix, which is real and symmetric with distinct eigenvalues, into the product of Q, D, and Q transpose. Again, where Q is orthogonal, D is diagonal, with the eigenvalues and eigenvectors comprising those matrices. Now, in the more general case, if our matrix has linearly independent eigenvectors but not necessarily orthogonal, then our diagonal matrix D was equal to U inverse times A times U, in which case, when we flip that around, we get this decomposition. So our matrix A is the product of U, D, and the inverse of U. Now the difference, of course, is that U is still a modal matrix, has the eigenvectors along its columns, but they're now linearly independent. They're no longer necessarily mutually orthogonal. And then finally, for a non-symmetric matrix with repeated eigenvalues, remember we get the Jordan canonical form. Once again, we can think of that as a decomposition because J is equal to U inverse times A times U. So once again, we flip that around and we decompose A into the modal matrix U times the Jordan canonical form J times the inverse of U. As you can see, this state of affairs is a bit confusing, first of all, and in some ways not terribly helpful, because in order to know which of those three decompositions to use, we need to do some additional analysis. We need to know something about the eigenvalues, for example, in order to know which of those decompositions is going to apply. So that's somewhat unsatisfactory in terms of a decomposition. We'd like it to be as general as possible. The other big limitation is this only applies to square matrices. And certainly many of our applications do involve square matrices, but there are many situations that we'll encounter throughout the book that do not. And so this is a very limiting aspect of the eigen decomposition. So I'm going to briefly in this video discuss the Schur decomposition, and then the next couple videos we'll be discussing the very powerful singular value decomposition, which is the basis for a lot of the applications and methods that you'll see throughout the remainder of the book, and also a more specialized version of the singular value decomposition, which is polar decomposition, which is used often in continuum mechanics. So our main focus will be on SVD, or singular value decomposition, but I'll mention these other ones as well. Also, at the end of the chapter, we'll discuss the QR decomposition. I've mentioned this a few times before. The QR decomposition itself provides an algorithm for actually determining the eigenvalues and eigenvectors, and this is the way that most mathematical software does obtain these eigenvalues and eigenvectors for matrices. We'll also encounter some additional decompositions later in the book, namely in Chapter 6. There's the LU decomposition, which is used for solving systems of linear algebraic equations, as well as Cholesky decomposition, which is a more specialized decomposition that we'll discuss at that time. The Schur decomposition is actually a generalization of the first eigendecomposition we just discussed a moment ago. And it looks like this. So it's slightly different. Before we had A was Q times D, a diagonal matrix times Q transpose. Now it's A is equal to Q times R times Q transpose. It's the same Q. So the columns of Q are the orthonormal eigenvectors of A. But now R is a right triangular, or we can also call it an upper triangular matrix. So this, in a sense, you can think of as triangularization rather than diagonalization. So rather than this being a diagonal matrix here, it's a triangular matrix. It turns out that the Schur decomposition exists for any square matrix n, even if it's defective. So even if there are fewer than n regular eigenvectors of the n by n matrix A, if A happens to be normal in the context of our discussion in section 2.4, and of course symmetric matrices are normal, then this will produce a D. So it'll be diagonalized. In that case, if it's not normal, then it will produce a right triangular matrix R. The process for getting the Schur decomposition is somewhat different than we saw for the eigendecomposition, although they're closely related. You'll remember the diagonalization procedure we discussed before. We needed the full spectrum of eigenvalues, and we need to get all of the eigenvectors, even generalized eigenvectors if necessary, to fill up our modal matrix U. In this case, for the Schur decomposition, we actually only need one of the eigenvalues and its associated eigenvector. We can then use something like Gram-Schmidt orthogonalization to get the sequence of additional vectors that are mutually orthogonal to form the Q. And what that means is actually the Schur decomposition is not unique. In other words, you could choose a different eigenvalue-eigenvector pair to start the process in order to get your orthonormal vectors to fill up the Q. So the Schur decomposition is not unique for that very reason. Now in practice, the way we actually get the Schur decomposition is through another decomposition, the QR decomposition. QR decomposition, it's the same Q and the same R. So Q is an orthogonal matrix, R is a right or upper triangular matrix in the QR decomposition. I won't go over it here, but there's also a really interesting proof, it's in the book, of Cayley-Hamilton's theorem, which we mentioned a few videos ago, and it uses the Schur decomposition as a way to prove the Cayley-Hamilton theory. It's pretty interesting.